We're going to be talking about continuous concrete beam design today. Many of you might have used our concrete section designer as concrete, and a continuous concrete beam design is really an extension of that, that we were going to talk a little bit more. So I'll introduce myself first. My name is Matt. Some of you might recognize me from previous webinars or training or even technical support. I'm in Vancouver, Canada. I work within the global technical team, and the team that I work with provides technical support, product demos, training, and so on to a variety of clients. I see many familiar faces in the audience that I've worked with before, but mostly on the S-frame products, and you'll see that there's actually a very large team in the global technical team that deals with all sorts of Altair products. Now, today we're going to be talking about S-line, which is really now in Altair licensing a part of S-concrete. So you'll start to notice me using those words interchangeably, S-line and S-concrete. We're going to look at the interface of the software, the code checking capabilities, as well as the auto design capabilities. And then we're going to go through an example that's using the ACI 318.19 design code. So you might be wondering a little bit more about S-line and the continuous concrete beam design capabilities within it. So I'm going to just elaborate a little bit more at a high level on what that is. And of course, we're going to go into more details in this presentation. So you can think of it as a standalone product that analyzes and designs and even details continuous reinforced concrete beams. Now it runs various code checks and it supports automated design. And it uses T beams, L beams, rectangular beams, and it can also design slab bands. It has the ability to automatically generate pattern loading with options for moment redistribution and so on. There are multiple design codes to choose from. As the email that you've received mentioned, we're going to go over an example using ACI 318.19, which is supported in the software. And it also includes automatic reporting, so you can get engineering design reports out of the software very easily without having to, click multiple buttons or generate a lot of information beforehand. And it's great for documenting your design and understanding how the software came up with that design. As you'll see, if you haven't used S-line before, it actually has a very handy visual editor, similar to what we've seen in S-concrete. It's actually developed by the same team. We can alter geometry, reinforcements, quantities, and so on. As well, it also includes the ability to assist with longitudinal beam modeling. And you can export to DXF files in AutoCAD, for example, and export PDF and Word documents. As I mentioned already, we do now support the ACI 318.19 design codes. And if you're recently switched over to the Altair licensing system and you're still unsure about what tools you have access to, effectively you have access to S-line if you're on our Altair 1 licensing system. If you're using S-concrete, you have access to S-line now. It's bundled in with S-concrete. If you're using the structural engineer or the advanced structural engineer suites, you also have access to S-line. So we'll go over later on some of the ways that you can access S-line, and hopefully this will help you learn a little bit more about the tool as well. So again, we're going to do an overview of S-line and get into the interface of the software. We're then going to talk about code checking for continuous concrete beams and look at beam design. So basically setting up kind of some initial parameters and letting the software try to optimize the design. And at the end of the presentation, we'll also go over an example that's solved by hand and is part of a verification example package that we're currently working on. We're going to be publishing shortly. So we've kind of already talked a little bit about this, but as you already understand, S-line is able to code check and design reinforced continuous concrete beams. It does support a variety of international design codes, and it has a very powerful user interface. If you're familiar with S-concrete, it's very similar to that. There's hotkeys within the software that allow you to click and drag reinforcement locations or the dimensions of your beam, the bay lengths, and so on very easily. I'd also say, like S-concrete, that the help system is very comprehensive, especially since there's a lot of code interpretation within the software, understanding how the software handles certain provisions within the design code is oftentimes the best place to look for that is within the help system. So we'll talk a little bit about that as well. So here's an example of the interface with just a file open here. This is a beam that you can see some different depths, and we've got a girder supporting it mid-span with a few columns as well. I'm going to walk you through the interface and hopefully help you understand a little bit more about where things are before we jump into the software and a live presentation. So here I'm basically highlighting with this orange circle here the visual editor window, and this is giving us an elevation or a section view of our structure, or our beam in this case rather. You'll notice here that we have several boxes for each of the bays within our model. So this shows us information on the span geometry, any code check results that we might have run already, and the types of boundary conditions or supports underneath that specific portion of the bay. At the bottom of the screen, we have the status bar. And again, I'm going to keep referring back to S-Concrete because I know a lot of you are S-Concrete users. The status bar in S-Line is very similar to the status bar in S-Concrete. When you run a code check, it will update you, and it gives you basically, I like to think of it as a stoplight kind of format. Red is bad. You want to stop what you're doing and try to address whatever the problem is, which the report that we'll show later will help you identify. Yellow is use caution. You're probably fairly close to passing, but there's still some attention that needs to be paid to potential design code violations. And green is good. You can proceed with that design so long as you're happy and you're not over-designed. We have various input data that can be entered not only from this data bar here, but also from the edit menu that you'll see me using later. Some analysis and code checking and preliminary design tools, and some result viewing tools as well. As you can imagine, we're running a structural analysis in S-Line, so we want to be able to view moment diagrams and torsion diagrams and deflection diagrams and so on. So I'm going to jump into an example model right now, and you can choose, or if you're following along, you're more than welcome to, but I'm going to just be using one of the default examples that S-Line comes with. There's actually quite a few, I would say, preview models that you can work with, but this one here that I'm going to be doing, this one is just a simple 3-span beam, and you can see that it's supported on the top and bottom by columns. So to really, the way I like to explain the interface is to work through kind of a sequential order that that users might encounter. So I'm going to go start first with the edit menu, and I think that you can do a lot of what you need to do in terms of setting up your model within the edit menu here. So I'm going to start with the general information button and drag this over. So this particular example is using the CSA code. But we can see here that this allows us to not only specify our code, our bar type, our units, and so on, as well as the base, the number of bays and so whatnot. We can also specify our material properties for concrete, for steel. We can specify other parameters as well as custom bars. So if we're using a bar size that might not be commonly used within the types of bars that are currently supported, you can define your own custom bars, and the software will consider those during the design checks. I'm not going to make any changes here, but you can see the different parameters that can be adjusted if required. I'm then going to go to the member configuration dialog, and this helps us specify more information for our geometry, I guess you could say. So here under the member configuration, I have 3 tabs, one for B1 or Bay 1, B2, and B3. So each bay is given its own tab that I can adjust independently. And we'll notice here, if we look at the labels, B1 is this one on the left, B2 in the middle, and B3 on the right. So we can always see those labels there. And I can see, first of all, the denotation, the length of the bay, which I can adjust here or through the visual editor window, the type of section that's being used, as well as data on the dimensions. I have section property modifiers, so if I wanted to modify this effective section properties for the effects of cracking, for example, I could do that here. I also can control the boundary conditions. So I have the option for a support above and a support below. I can specify what type and size of support that is, and then the actual boundary condition as well. whether we want it to be pinned or fixed, depending on our own specific requirements. And again, each bay can be adjusted independently of one another. Now, the third option from this list is reinforcing styles, and this is where we start to get into a little bit more detail. So here I can see that under the reinforcing styles, I have 3 different styles that I can work with. I can go with, for example, different top bar styles. We have different tabs at the top to describe the different reinforcement styles we might want to apply, and different parameters related to this. And you can see that we can actually save these styles, and we are able to go through and recall them at a later time. So here I can see the top bars, the bottom bars, and miscellaneous bars, which include clear cover, stirrups, length distribution, and so on. And once I enter all these parameters and I choose the top bar style and the bottom bar style and the miscellaneous reinforcement details that I'm interested in, I can then click OK, and it's going to apply all my reinforcing styles. So you can see here that it's initialized this data. It may not necessarily be exactly what we want to end up with, but it gives us a good starting point to start adjusting. So you can see that now we've got our stirrup spacing, our longitudinal reinforcement, our bar cutoffs, and so on defined based off of those initial parameters that we've set up. And we can fine tune that using the interface here. The visual interface allows us to adjust these dimensions, for example. We can also go into the edit member reinforcing dialog. And in the member reinforcing dialog here, it's a bit of a behemoth, I'll admit, when you first see it, but it does offer a lot of control. And I think it's really best explained in a PowerPoint slide. So let me just quickly go back to my presentation, because I think this would actually maybe intimidate new users if they didn't know where everything belonged. As you are potentially a new user of S-Line, we wanted to make sure that you understood this. So I've extracted a copy of that reinforcement spreadsheet here, and we're going to look at it more carefully. And maybe to help, I'm going to just enlarge this icon at the top. You can see this yellow icon here that's a bit of a schematic in terms of where everything is. And this will hopefully help us better understand. So there are basically 6 groups of bars defined for every beam. We have A to F and B to C. Oh, sorry, A to F, and the B and C bars, A, B, and C bars on the top, and the D, E, and F bars on the bottom. And we can correlate that information with our beam. So obviously we have on the left side A, C on the right, and every bay, depending on how many we have, will correspond to that. Now, if we look at these spreadsheets a little bit closer, we can see that every single section of our beam has 4 different potential bars that we can define. So we can have A1 and A2 bars, A3 and A4 bars, for example, in this A section. And what that allows us to do is basically specify different quantities and also bar sizes within the same layer. So we can have a first and second layer within the A section, defined by A1 and A2 for the first layer, and A3 and A4 for the second layer. And the same thing applies for the other layers as well. So this hopefully makes a little bit more sense once we break this down into a section view. And with the section view here, I'll try to correlate this with what we have shown here in the longitudinal top left bars. Here's our first layer. There's our second layer. We have A1 on the far outside and A2 in the middle. And an A3 on the bottom and A4 in the middle bottom as well. And obviously the same paradigm applies for the lower layer or the bottom side of the beam. Of course, these are going to refer to the D bars, which again are the bottom bars on the left side of the beam. You'll also notice here that we have the ability to define extensions within our reinforcement. So for example, the A2 bars, we can extend beyond the actual A section, and that might reflect what's shown in the B2 bars, because you can imagine A will go into B. So those two are somewhat correlated to one another. Now the actual, I guess, Edges of these reinforcement zones are usually defined by the nearest column or support, whether it's a girder or some other type of support, center line. And for the center bars, it counts at from the base center line. So hopefully that clears things up a little bit more. I'm going to go back into S-line and just explain here at the bottom of this dialog as well, we can define parameters related to face steel, our clear cover, our spacing between the layers, as well as our shear spacing for our stirrups and whatnot. So we can define different sets of stirrups and different spacing and obviously bar sizes as well, number of legs and whatnot. Just moving down to the last few points here, member loads. If I go through this, we can see that we can define 4 different types of loads. We have distributed vertical loads, distributed torsional loads, concentrated vertical loads, and concentrated torsional loads. And these can be defined on a zone-by-zone basis for dead, live, or what we call other loading cases. So if you wanted to consider, for example, like an offset load or an off-centered load, you can define that as a torsional load, perhaps a concentrated or maybe a distributed torsional load, depending on your own requirements. I addressed that because there was a question that came in before the webinar on that very topic. And under the load cases and combinations dialog, here we can see that S-line is going to automatically generate pattern loading for all of our different loading scenarios, as well as create our serviceability and strength load combinations that can be considered for deflection checks, for strength checks like shear, and bending, and torsion and whatnot. So we can control that here. Now, for those of you wondering, this example I'm using is using the CSA code. I will be going through an example with hand calculations as well in the ACI code towards the end of the presentation. So if that's the code you're using, hold tight, it's going to be coming up soon. I did also just want to mention as well that the help system, which you can access, and I'll show you that later on, through the help menu within S-line, has design code specific support pages, but there's also other resources as well, online support. I'll refer you to that at the end of the presentation so you know where you can look for that information. Now we're getting to some more of the, I guess, the exciting parts, the code checking in S-line. So once you've actually had a section or a beam defined and you specified your loads and your geometry and your reinforcement and so on, then you can move on to code checking. Now, obviously, you have to define your member loads first, and we talked about the different types of loads that are available, and your load cases and combinations will obviously reflect that as well. You'll then be able to analyze and code check the section, or the member rather. So S-line has a built-in structural analysis. That's where it's a little bit different than S-concrete, as you know, because it is a beam and we are applying loads to it. It's actually running a structural analysis for us, and it can consider things like moment redistribution and whatnot. Obviously, when we run the code checks, we want to be able to account for that information and document it somewhere. So the engineering design reports that are produced will show us all the different calculations that have gone in. The code violations, if they exist, will also be listed at the bottom of the report as well. So let me just do that right now. I'm going to go through this existing S-line model, and I'm just going to go to the Run menu. And without changing anything else, I'm going to say Analyze and Code Check. So just click this button here. And unlike S-line or S-concrete, because it does have to run an analysis, we need to specifically prompt it. So we're going to click OK, and it's going to run the analysis, generate all the moment, shear, and torsion diagrams, and deflections, and so on. And then you can see here now I have my utilization ratios at the bottom of the screen. So my overall warning status is basically indicating to me that I might be passing all of the strength checks, for example, but there are some other violations within the code. They could be detailing related, they could be related to something else that I would need to study. But as we can see here, the utilizations on this particular beam set of beams is rather small. So my shear utilization is about 18%. My positive moment, negative moment utilizations max out at around 30%. So this is a ratio of the demand versus the capacity. And I can actually look at each beam individually, or each bay, and I can see here that the two outside bays are more highly stressed, at least in terms of negative bending. So I would need to study that a little bit more. Now we can look at the results under the results menu here. I can look at the report, which I'll get into shortly, but I can also look at things like the deflection diagrams. I see there's actually a question in the Q&A section about deflections. So S-Line does calculate deflections for us, and we'll see later on it can do short and long-term deflections. But here I can see that it's showing me on a bay-by-bay basis the deflections within my beam. And I can actually scroll this ticker across and see at a specific location what the deflections are at, for example, x equals 3,500 millimeters. So I can see here that it's showing me for load combination number 1, I have about 0.5 millimeters of displacement. Now the maximum displacement I get here is load combination number 6, and I can see here that it's negative 1.2 millimeters. At the top of the screen, we also have the ability to view moment diagrams. So I can see all of my the gray lines represent my different loading scenarios. I also have around these gray lines my moment capacity envelopes. So I can see how close I'm getting. If I'm failing, it would be outside of those blue lines there. And these green lines indicate my maximum and minimum or maximum negative values. I can also view shear, and I can see torsion here to get a little bit more information. And of course, this information is available for all the different bays within my model. If I wanted to study this even closer here, I could go to the analysis model. And under the analysis model, I can see the actual structural analysis model with more information about the material properties that have been used and the section properties and so on. I can also see the loads that have been applied. And I can study this in more detail, and I can see, okay, well, here is my load combination number 6, dead plus live 1. And I'm looking at immediate deflection in this case here, and I can see what I'm getting throughout this, this beam structure. And I can look at net long-term deflections as well and see the effects that those have. And more information is available on this within the help system in S-Line. Now this all helps us understand the demands on our structure in terms of deflections and moments and shears and whatnot. But to understand the actual design checks that have been performed, what's really useful is the design reports. So under results report, we can see our engineering design reports. And I have 3 tabs at the top. And you'll notice similarities if you've used S-Concrete to these types of reports. So here I can scroll through this, and I can see here that I've got a variety of details related to my specific beam. So in this case here, it's showing me that all these green icons, I guess you could say, are showing that it's acceptable based off the code provisions. So my moment results, my shear and torsion results, and so on. But then I scroll down and I start to see some yellow. So this yellow is indicating message 8, and it seems to be related to stirrup spacing. I'll keep scrolling. And as I get to the bottom here, I see that there's a list of messages, and it's just letting me know the shear reinforcement spacing exceeds the allowable. So here it's telling me that I have the applied or the recommended stirrup spacing here and the maximum that's allowed. And so I would need to study this a little bit more and determine exactly what the issues are. But you can see this is all documented for us, and it's very clear what would need to be done if we needed to make changes. I'm not going to touch on that right now because the next topic is actually one where we're going to be making some changes. But as you can imagine, we can go to the edit menu and we can go to member reinforcement. And if I wanted to, for example, tighten up my stirrup spacing, I could change those spacings for each set of stirrups in each one of my bays if I wanted to. So we have full control over that. We can also obviously change the stirrup spacing using the hotkeys within S-Line. So for example, I can see here that in this bay, I have 5 stirrups at 375 millimeter spacing in the middle. I can left click on that and it will decrease the spacing, basically adding more steel, just like S-Concrete. I can do the same thing here with the number of stirrups, and it will go to 6 stirrups rather than 5. And obviously the stirrup spacing will change as well. So you can see some similarities between the 2 interfaces. We can make changes very quickly that way. So something that we touched on earlier in the presentation is the pattern loading that was generated. That's done automatically by the software. We can also consider immediate and long-term deflection checks. And our verification example will touch on that even more. We can look at detailed deflection, force, and moment diagrams that would consider moment redistribution. And all of this also ends up in our design reports as well. Now, the next topic we're going to discuss is concrete beam design. And where this might differ from the previous topic is we're actually going to look at how S-Line's auto design capabilities can be set up to give us kind of a preliminary estimate for what our design might require. So we can specify user-defined constraints. And this basically allows us to have control over the design process in such a way that we might want to limit the bar size that's being considered by the design algorithm, or we might want to limit what the design algorithm can adjust, whether we want to freeze certain parameters to keep those similar or the same as our original guesses. And what we'll end up with is basically suggestion for our future design. Now we can go through this process manually, making changes like I mentioned, changing the stirrup spacing by left clicking on our visual editor window or from the dialogues themselves, but it can also be automated, and that's what we're going to be talking about next. And it is a transparent process. We document all the changes that we make so that there's no surprises. It may not necessarily come up with the same solution that you would agree with, but it will get you closer to a passing solution that helps you kind of get you in the right ballpark. So I'm just going to re-code check this because I made some changes earlier. Remember, I changed the stirrup spacing. So I'm going to click the start button and re-code check. And you can see here my utilizations are fairly low. So what I can do is under the run menu, I can go to design constraints. And here I can focus on, again, individual bays if I wanted to. And I can specify the maximum and minimum depths of my section if I wanted the software to change that. So we could always make that change. I can also freeze the depth if I wanted to. And here we can see all the different bar groups and stirrups and base steel even can be controlled and frozen or given windows of adjustability that can be considered. So we can see that we do have quite a bit of information here that can be specified to allow us to kind of unleash the design algorithm as we like. And once we're okay with it, we can click the OK button and then we'll get the preliminary design set up. And I like to just emphasize the term preliminary design because it's not necessarily going to come up with a design that is going to be exactly due to your intentions. You're the engineer behind this, so obviously you might have your own opinions on how it should be done, and there's no problem with that. The software can certainly let you adjust and tweak it as you need to afterwards. Now, this particular example, I'm not actually failing any of the code checks in terms of structural demands, but what we can do is we can either step through the design and S-Line can make changes, or we can press the auto button and it will do up to 6 iterations at a time. So you can see here that it actually, with the first step, I was able to get a solution here that was deemed acceptable, meaning that it was able to change that stirrup spacing to satisfy the code requirements. And we were able to see here all the different parameters that have been changed. So first of all, it changed the width of the section. It went from 400 millimeters to 375 millimeters. It also changed the bars that were used in each of the beams. So here in A, everything except for the clear vertical spacing was changed. And same thing actually with all the other locations as well. So a lot of these parameters have been changed slightly and it's all noted for us. And so I can see now my overall acceptable status has changed. It's gone from a warning to an acceptable status. My shear and torsion utilization has gone up, but it went from 18% to 24%, so not really a concern yet. And my positive moment and negative moment utilizations have also gone up, actually more than the others. Now, for some, they might consider this still to be over-designed, and that's what I want to stress. This isn't meant to be, the be-all and end-all. You can continue to tweak this as much as you like, using the different parameters that you have available to you. So obviously, you could change the bar sizes, for example. You go maybe with a smaller number of bars, so from 3 to 2. You can do that just like you do in S-Concrete. and rerun the analysis and the code check. So I know that was a fairly quick section, but again, I think it's worth touching on. It allows you to quickly optimize your beam design and get you to a ballpark location where you're able to then say, okay, you know what, I'm satisfied with its results, but I want to tweak it a little bit more, maybe to optimize it further. Something I haven't touched on yet is your ability to export reports, like those design reports that we saw, and images of your sections and your beams and whatnot to Microsoft Word if you want to document that information there. We also can obviously print off those engineering design reports to a PDF file or to a paper printer if we like. And we can send this information to a DXF file, which is great for further engineering documentation. For example, if you wanted to document the reinforcement and so on in a drawing, that might be a great option for you. So this next example is actually using a verification example that some of my colleagues have been working on. So we're going to be publishing these verification examples shortly, but hopefully this will give you a bit of a preview of what they cover and show you some of the calculations that are done within S-Line. Now, for a bit of a description on this particular problem, it's a simply supported beam, and it has girders on each end. It's a T section, so you can see the dimensions of the section there, and we have the reinforcement shown at that section cut. And we're going to be examining the reinforcing design and detailing for bending moment, shear, and also torsion. And also looking at the effects of immediate and net long-term deflection estimates. Now, we also need to understand our loading that's going to be on this particular section. So in this particular beam, we have vertical distributed loads, and you can see what those work out to be here. So our total dead load works out to be 1.67 kips per foot, and a live load works out to be 1.4 kips per foot. And we also have some concentrated torsional loads as well. They're located at different positions on our beam, so at the quarter point, the half point, and the three-quarter point. And you can see the magnitudes for each one of those. They're all the same, just located at different locations. So you can see your design load summary before it's factored and after it's factored, what those magnitudes will be. So I'm just going to jump into the software just to kind of explain again what we're dealing with here. So I've got the model ready to go. I'm not going to save this file. And this is what we're dealing with. So as you can probably remember, the magnitudes of these loads here that we're showing, I've got them here. So our dead loads, our live loads, and then we have, in this case here, we just have one bay. So, you know, the different loading bays and so on won't really be relevant. But they're obviously all being considered there. If I go into the general information dialog, here we specified our building code to be ACI 31819. Our material properties for steel and concrete are also shown here. And we can see our bar type, we're using the American bar type and US units, just to clarify in case there are any confusion since we're using metric in the last example. Under member configuration, I can see the dimensions of this section. So it's a T-beam that we're using. You'll notice here that we've got, again, we're assuming the end conditions are fixed, but it's supported by a girder underneath. So you can see the dimensions of that girder as well. And actually what I did want to show as well is if I go to, you'll notice here I have this section view location. I can move this to anywhere on my beam that I like, and I can click on this view section button here. And when I do that, I'm able to see the beam and the different cross sections that might occur along that length of the beam. So in this particular location where this section view is, I have face steel. So you can see the location of those face steel and the size of the bars and so on are shown there. But I can move this anywhere else in my beam and it will update based off of those different parameters. So we're able to see the changes as we scrub across our beam. So the total length of this beam is 36 feet. And you can see again the dimensions of the beam, the supporting girder, sorry, that we're dealing with. Now I've already run the code checks ahead of time, so you can see some of these parameters listed here. But I'm going to go back into the slides and we'll talk a little bit more about some of these parameters. So concrete material properties, to just explain a little bit more how we're coming up with this. So we have our Young's modulus of concrete, our shear modulus, our lambda factors, and our modulus of rupture, with all the clause references as well shown there. For the section properties, you can see, well, there's quite a few. I won't touch on all of them because it'll take me a while to go through that. And frankly, I'm sure you guys can obtain this data. We're going to be publishing these verification examples as well, so you'll have access to this. But you can see some of the values that are calculated for us. These will all reflect in our design checks later on. So you can see our crack moment in the negative and positive directions, our effective depth and whatnot. Now for our analysis model, we have the finite element model that was created based off the geometry that we defined and the applied loads. And I'm just showing an example below from load combination 8, which has got 1.2 times the dead load plus 1.6 times the live load. And we can see the shear forces, the moments, and the torsion diagrams. Now it's worth mentioning here that girder supports, actually by their nature, are pin supports in this structural model. The girder is not going to have any torsional resistance. So the critical sections for design are taken at the face of the girder, which is 12 inches at each end from the full span length. That might come up in some of the later calculations, so I did want to just mention that before we get too far along. Now here's some information on the bending moment evaluation. I'm not going to talk about every parameter again, but I do want to just mention that S-line considers the top steel for positive moment calculations when the depth of the compression block A falls above the top steel layer. And S-line also provides an option to include face steel in the moment capacity, if that's something that you'd want. So this is the design moment for load combination 8, I believe it was. You can see here the magnitude of the demands at X equals 216 inches from the face of the support. And this is our moment capacity that we're going to be dealing with. As for shear evaluation, we're looking at shear at the critical point X equals 374.4 inches. And the design shear forces and moments with this loading scenario here, we have 56 kips at 374.4 inches. And our torsion, which would be 19 kips at X equals 374 as well. Now, according to clause 9.4.3.2, the beam shall be permitted to be designed for the view of the critical section located at a distance of D equals 25.63 inches from the face of the support. Now, in this member design, due to the variable spacing of the stirrups along the member, the controlling section for shear wasn't actually located at the member end. But you can see here the shear capacity that we're working with, 85.2 kips. Next, we'll move on to torsion. We already mentioned the torsion. I think I forgot to include the point after the decimal. So it's actually 19.8 kips is our torsion demand at 374.4 inches from the face of the support. And you can see the capacity that we're working with. So we have 36.1 kip feet. And at the face of the support, or within the distance of the effective depth from the face of the support, the applied factored torsional moment is 19.8 kip feet, which exceeds the 0.25 feet times the torsional cracking of 16 kip foot. So therefore, we must consider torsion during the design. And that's what's highlighted here. So overall, when we're looking at the shear and torsional utilization, we have the following utilization formula that's being considered, considering both shear and torsion. And our utilization ratio works out to be 0.745. Less than 1, which is what we wanted. So that's an acceptable design, so we're happy with that. We also want to look at the longitudinal steel reinforcement and the requirements related to that. So we'll focus on the bottom bars. And I will admit, I'm kind of pick and choosing some of the parameters of some of the components of that verification example, just for the sake of brevity, because I don't want to spend too much time going over every detail when this will be published later. But here we can see the longitudinal steel required in the bottom bars at x equals 100 inches. So we have 6 number 8 bars, which equals 4.74 square inches, and it's greater than the required steel area, which is deemed acceptable. And when we're looking at the top bars, again, similar calculation. I'm not going to go into too much detail, but we can see that the applied steel area is 1.73 inches squared. Now looking at stirrup spacing. So for first segment, x equals 12 inches here, we can see our demand for shear 63.1 kips and our shear capacity 87.1 kips at x equals 12. And we've noted that shear reinforcement is going to be required. So we've got 5-inch spacing, which is less than the maximum required for segment 1. And similar to segment 2, we just got a different spacing. We have 7-inch spacing here because of the way the shear diagram slopes. We have less shear, so less shear reinforcement demands. So we're getting away with slightly wider spacing. Now for segment 3 here, we've actually found that shear reinforcement isn't required based off of the demand versus capacity relationship that we see here. So we can move on to deflection evaluation. We're calculating the crack moment of inertia, and I should again mention here that there are a few aspects to this calculation that I haven't gone into. So this isn't a complete overview of the entire verification example. It's kind of picking and choosing the points that that we wanted to showcase here in a quick amount of time. But you can see here that we're calculating the crack moment of inertia in both the positive and negative axis. And this information will help us determine the immediate dead load deflection, which equals 0.754 inches. We can also look at the total immediate deflection, which is dead and live. So it equals 1.5 inches, and the immediate live load deflection will equal 0.746 inches. So you can see here that that's basically just the difference between the dead and live minus the dead loads deflection. So 0.746 inches, which is less than our deflection limit. Now, when we're looking at net long-term deflection, dead plus live loads, we've found that the net long-term deflection here equals 1.1 inches, and this includes shear deflection in the estimations. So I'm just going to go back into the S-line model and kind of show you where some of that information was found. Probably the easiest spot to look would be in the results report, since it's all documented there for us in one spot. We just have one base, so it's easy to know where to look. But here we can see, first of all, that our negative and positive moment utilizations are all satisfactory. We can see the information about our bottom and top reinforcement for our longitudinal steel and whatnot, as well as our shear and torsion results. You may remember we also laid out our stirrup spacing. So we found our stirrup spacing 5 inches in section 1, which is closest to the support. Section 2 had 7 inches, and we didn't actually require any stirrup spacing in section 3. So that's why the stirrup required option says no here. And let's continue scrolling down here and look at the deflection requirements. So you may notice here the immediate live load deflection that we were getting, 0.754 inches. Hopefully that raises a memory for you. 0.754 inches is less than the deflection limit criteria that we had. And our net long-term deflection worked out to be 1.114 inches, again, less than that capacity that we had. So let me jump back into the slides here. This is kind of wrapping up the presentation. I know there was a lot of questions we'll try to answer later on, but to maybe summarize what we've talked about with S-Line, which again is now part of S-Concrete, It does allow for customizable geometry and loading. You can define your own load cases and combinations, and you can control the patterns that are being used. It also does run an analysis, and that might be where it differentiates from S-Concrete. So you can run an analysis and then run code checks on top of that, and even an optimization. So if you want to arrive at a preliminary design state and you're not really sure what changes to make, you can always make those changes, or let the software make those changes rather. And just like S-Concrete, you're able to then output detailed and transparent engineering design reports that document the design process and the intermediate calculations and clause references that have gone into the actual design itself. So I know there are a few questions that came in. We'll do our best to answer as many as we can in this presentation. So one of them was related to considering crack behavior of concrete. So I did mention there is the ability to define effective section modifiers. So that's under the edit, sorry, let me just make sure I got the right name, edit member configuration dialog, which I'll show later on. You can define effective section modifiers for like the moment of inertia and so on. There is a question asking about if we can show an example on concentrated torsion. So that one might be best referred to if you do have access to S-Line or S-Concrete. There are actually different built-in examples that I can share with you shortly that you can go through and see how those are defined. On that same topic, there is a question actually that plays into one of the comments I was going to make later about what is the difference between S-Concrete and S-Line, because I have mentioned them together quite a bit, and it just so happens we just created a community article post that I'm going to share in the chat window here. So if you have access to Altair 1, you can actually search for this, but let me just try to share this link here in the chat pane. You'll be able to see a bit of a description on the differences at a very high level between S-Concrete and S-Line. Now they're basically part of the same license, so you're able to actually use them as you see without having to purchase one separately than the other. Okay, I'm gonna close the poll now and get back to one of the comments that came in earlier. So one of the questions that came in was about applying loads. So if I go to the edit menu and I go to member loads, you can see that we have these different options here on the left-hand side, and they were asking specifically about concentrated torsional loads. So in this case here, there are 3 different concentrated torsional loads within this particular model. So each one was given its own row, and its location is defined, and then whether or not it exists in one of these load cases, it's going to be entered there. So hopefully that clears things up. Again, you can define this however you like. You can have one at 0.83, and it might only be in the live load case, and it might be a magnitude of 5 kip feet. So you have full control over that and how it's entered. There was another question asking about two-way slab design in S-Line. So S-Line is a 2D program, so fortunately you won't be able to do two-way slab design. I would say S-Frame would probably be your best bet for that. We do actually have another webinar that we'll try to make available down the road on S-Frame slab design capabilities, because I think that is usually a popular webinar when you held it in the past. Another question that came up is about the preliminary design results. You may remember when I was going through that last example, which unfortunately I forgot to save, it suggested some changes, and obviously we're giving it some free rein to kind of do what we want it to do. But the reality is that that's just a suggestion. Nothing is set in stone. That doesn't automatically get printed to a report or anything. It just gives you kind of a new starting point or a new point that you can then modify beyond that. So you don't have to accept it. You don't even have to, you can go back to what you had before if that's what you like. But it does sometimes help you arrive at a conclusion maybe faster if you're not really sure what changes need to be made. There was another question asking about whether or not in the auto design capability, you're able to not use the 2 and 4 reinforcement categories. They just want to use 1 bar size within each layer. I'll have to double check on that. I'm not sure off the top of my head, so I don't want to give you an answer without knowing 100%, but let me circle back with you on that, and we'll try to give you some more information. All right, maybe what I'll do just while there's some more questions here, but I don't know that I'll be able to necessarily answer all of them. Maybe I'll just do one more here. So they're asking about boundary conditions and supports and area loads. So first of all, I should mention that, again, just reiterating, we don't have like a 3D analysis within S-Line, so it would actually have to be converted to a distributed load, like a distributed vertical load, so kips per foot or kilonewtons per meter, whatever unit system you're using. That's done under the member loads. And under the edit menu, if you go to member configuration, here you can specify the type of boundary conditions that are used, depending on what you're working with. So you have control over that, and I encourage you, if you have access to S-Line already, to take a look. So I'd like to thank everyone for their time. Again, we look forward to seeing you at future webinars and trainings and keeping in touch. So thank you.